Alright, so now let's talk about our functional groups. A functional group is a chemical unit that you can pop onto an alkane chain in order to change its chemistry. Sometimes these changes can be small, sometimes they can be really, really big. In order to attach a functional group, you have to first remove something that's already going to be on there. Carbon really hates not having four bonds, whether that's single bonds or double bonds or what have you. So this is known as substitution. Okay, you're removing a bond in order to attach your functional group. Usually this means, not always. I'm not even going to say that. Sometimes it removes hydrogen, sometimes it substitutes a functional group already there, sometimes you are replacing a double bond. Doesn't really matter. These here are our functional groups. You have, this is going in order of priority. From no priority whatsoever are halogens. A haloalkane, that's when you have fluorine, chlorine, bromine, or iodine on your alkane chain. Next up is your amino groups, or your amines. That's when you put an NH2 onto your alkane chain. Then your hydroxy, or alcohols, with an OH group. Your alkoxies, or your ethers, when you have two alkane chains joined by an oxygen atom. Then you have your terminal carbonyl, or an aldehyde. That's when you have a carbon double bonded to an oxygen on the end of your chain. A non-terminal carbonyl is a ketone. That's when you have a carbon double bonded to an oxygen in the middle of your chain. Next is a carbonyl plus a hydroxide. That is a carboxylic acid. Because the carboxylic acid takes up all but one of the carbon bonds, this can only ever come at the end of a chain, although there are ways of getting more of these into the name of your compound. So it's always terminal, COOH. Carbon double bonded to an oxygen, then single bonded to another oxygen for a hydroxide group. And finally, if you have basically, more or less, a carboxylic acid in the middle of your chain, you have an ester. That's when you have a carbonyl plus an ether. So those are the functional groups we are going to be covering, but that is definitely, or actually, no, there's one more. I'm sorry, there's an amide as well. An amide is when you, instead of a carbonyl plus a hydroxide, you have a carbonyl plus an amino group. That is an amide. And those are the functional groups we're going to be covering in this class. That is an incomplete list. You can get more, and you can combine these in other ways. That said, let's go ahead and talk mostly about the chemistry, touching lightly on reviews of the nomenclature. First up, we have our haloalkanes, or alkyl halides, as they're sometimes called. This is just an alkane with one or more halogens, fluorine, chlorine, bromine, or iodine, substituted onto them. These guys have low reactivity. They used to be used as refrigerants and repellents. And as I say, you'd find them in refrigerators and air conditioners, or in hairspray and so on, because they have low reactivity. I mean, in a way, these seemed perfect when they were discovered, because they're non-toxic, they're non-reactive, and they are non-flammable in and of themselves. They have low flammability. Problem is that, I can just show you one. Here it is. You see it's been fully substituted with chlorines and fluorines. So this right here is part of a class of compounds known as chlorofluorocarbons. You might recognize that, therefore, as the thing that destroys the ozone layer. So, haloalkanes have fallen out of favor in recent decades because even though they were, sort of the perfect answer for refrigeration and so on, now we know that they are really, really bad for us in the long term. And so Now they are principally used as intermediates. You pop a hydrogen off, you pop a halogen on, and that changes things very slightly. Because your halogens are more polar, or more electronegative, I should say, than carbon. So it puts a region of polarity on the molecule, so that the halogen or the carbon can be attacked by various Lewis acids or Lewis bases, depending on what you want to do. These are kind of common in the environment and in medicine. Not so much in nature itself. Some bacteria and things will make some haloalkanes, but not very many. This is mostly a human thing. When it comes to naming them, a halogen never has priority. It's never a suffix group. It is only ever going to be a haloalkane, only ever a side chain. And next up in our litany of functional groups, we have the amines, or the amino groups. This is just an NH2 attached to an alkane chain. And what this is always going to do is give some basicity. It makes every alkane a weak base, because the amino group can always attack, or it will always be able to accept a hydrogen, or it will always be able to donate a pair of electrons to things. So it also makes these things polar. It's going to make them soluble in water. It's going to make them kind of stinky. They're going to smell like ammonia. These are a very broad class of compounds that are always incredibly important in biology. Down here in the lower left, you see we have pyrrole. Related to that, we have pyrrolidine. Above that, we have nicotine, which has two nitrogen compounds. These things love to substitute into rings, as well as popping onto chains. So nicotine is, you see, it has both an aromatic substitution, in that you have the aromatic ring there on the left, and a non-aromatic substitution. Both rings, each ring I should say, have a nitrogen on it. In the case of nicotine, I'm pretty sure that's a pesticide for the plant, as well as being an addictive drug for us. It shows up all over the place in things that are vital to us. On the right, you have proline. That's one of the amino acids. So you have the amino group and the functional side chain of the amino acid are both contained in that ring. And below that, you have one of the nitrogenous bases that links DNA chains and codes in DNA. This is adenine, which again has two different rings with multiple nitrogens substituted in. And then on the left-hand side of that double ring, you have it's linked to the ribose backbone of the DNA chain. On the right, it forms hydrogen bonds with, in this case, thymine, to link it to the other DNA strand. So amines are vital to biochemistry and organic chemistry, is what I'm trying to say. They're also vital to proteins, not just to DNA, but then proteins not only do they form half of the amino acid, amino, but they also show up in the active sites of enzymes. You get a lot of amino side chains there in the active sites. We know that they show up all the time. We're still not entirely sure as to how that makes the active site function in the way that it does. Or at least I don't know. There's active research ongoing in this. We want to be able to make our own enzymes. Amines are classed as primary, secondary, or tertiary. This is based on how many carbons are attached to the nitrogen. So if you have 0 carbons, of course you just have ammonia. If there's 1 carbon on that nitrogen, then it's a primary amino group. If there are 2 carbons, then it's a secondary amino group, and if there are 3, then it's a tertiary amino group. When it has priority, then when it's the suffix group, then it's an alkanamine. When it lacks priority, it's just an amino group. So you might have like aminoethanol, something like that. And let's move on. Number 3 is alcohols. This is an alkane with a hydroxide substitution, an OH group. An alcohol is going to make your compound polar. The oxygen is more electronegative than your carbon. So that's going to make it soluble in a lot of solutions, particularly water. It's going to increase the boiling point and the melting point, and this is going to increase the reactivity. It's also going to have the interesting effect of making the compound able to both give and receive H-bonds. So it's going to interact very strongly. It's going to have very strong intermolecular interactions, non-bonding interactions. The proton of the oxygen there, the hydroxide hydrogen, that is not an acidic proton. The oxygen also doesn't steal protons from, say, water. Most alcohols are not basic or acidic. You throw them into water, it's not going to change the pH. These are pretty hugely important in biology and biochemistry, as well as in organic chemistry. Here we have glucose, sugar, in both its chain and its ring form. And you'll notice that it is covered with hydroxides. All your sugars have lots and lots of hydroxides. They also have a carbonyl. They're either aldehydes or ketones in their chain form. In their ring forms, you'll see they're ethers. So there's other functionality going on there as well. But the hydroxides, the alcohols, are what we're focusing on here. They're called primary, secondary, and tertiary, similar to amino groups or amines. But it's a different sort of organization. Instead of how many carbons are bound to the oxygen, it's how many carbons are bound to the carbon bound to the oxygen. And so we're looking at not the hydroxide itself, but the carbon bound to the hydroxide. So if there's one carbon on that, it's a primary alcohol. So the hydroxide group is coming at the end of the chain. If there are 2 carbons, then it's a secondary alcohol. Your hydroxide group is in the middle of the chain. It's along the chain. And if there are 3 carbons bound to your hydroxide carbon, then it's a tertiary alcohol. It's at the middle of a branch. This affects the ways that alcohols react. So if you go on to study organic chemistry, it's important to know the difference between primary, secondary, and tertiary alcohols. When it has priority, then you're looking at alkanol for your suffix group. Without priority, it's just a hydroxy side group. And that brings us close enough to 15 minutes that I'm going to go ahead and call it for this one. When we come back, we will continue our discussion of the ever-fascinating functional groups.